Hello everybody, my name is Pablo Martinez. I am from the University of Murcia and I am going to present my work called Achieving Native Performance with a Simple Heterogeneous Programming Framework based on LLVM. First, I'm going to give you a brief introduction, then I'm going to talk about our approach called HPHL. Then we're going to evaluate our approach and we're going to end with some conclusions and future work. So computer architects are finding difficulties to continue improving the performance of CPUs, and this is essentially because the end of Dennard scaling and Moore's law. And to continue improving the hardware performance, the solution appears to be the heterogeneous computing, which essentially is to use not only the CPU, but also other devices which are designed to do specific tasks or to work in specific domains, like the GPU or the Google TPU. The problem with these devices is that they need different programming models and technologies to work. And the solution for this problem is to use single source multiple devices languages, which essentially are languages that allow programmers to have one single source code and that this code can be executed on different devices, for example, CPU and the GPU. The problem with these devices is that they add a significant effort and complexity to the programmer because the programmer often needs to learn new technologies and libraries. And there is currently no solution for this problem because this is ongoing research. And the second problem is that the performance that we can get from these languages is very far from the native programming of each device. And again, there is no solution for this problem because this is currently on research. And some examples of single source multiple devices languages are WinAPI, which is being developed by Intel, OpenCL, Cocos, or FAST. So LLVM is a well-known compiler technology that has been applied successfully to many kinds of compiler problems. And it works with an interesting idea of intermediate representation, which is a textual representation that this is between the source code of the program and the binary executable. And this intermediate representation allows for different kind of optimizations, but also allows a lot of flexibility in the compiler design. And there are actually many approaches to heterogeneous computing using LLVM. And some examples are HPVM or WinAPI. However, existing approaches suffer from one or two of the problems that I mentioned before. So our approach is called HPHL, which stands for High Performance Heterogeneous Language. And HPHL is a single source LLVM-based approach that provides a C or C++ interface for running heavy workloads efficiently on the CPU and on the GPU. So essentially, HPHL provides an extension to C or C++ code using functions. So in C or in your C or C++ code, you must include the appropriate header of HPHL, and then you can start working and calling these functions. And the thing with HPHL is that the performance obtained with this language is comparable to the performance that you can obtain using optimized libraries for its architecture. And this is because the overhead introduced by this language is zero because it always operates at the intermediate representation level. And at the moment, HPHL only supports general matrix multiplication. So how does it work? First, you have your source code. In this case, it is a general matrix multiplication. In C or C++, you must include the HPHL header. And this code, which contains calls to HPHL, must be compiled using a modified Xlang. And this will generate an intermediate representation file, which contains the intermediate representation from the C code, but also some HPHL intrinsics. Then this file must be transformed by HPHL, which essentially will replace these intrinsics by native calls to the CPU libraries or the GPU libraries. And this last intermediate representation file is again compiled with a normal C-line compiler into a native executable, with no dependencies from HPHL. So as I said, when you work with HPHL, you must call HPHL functions, and those functions are translated to an intermediate representation intrinsic from HPHL. And then in the second step, these intrinsic are automatically translated by native calls. So the thing about HPHL is that instead of developing new CPU or GPU backends, all the calls to HPHL are replaced by device-specific calls. For example, in the case of general matrix multiplication, HPHL calls are replaced by calls to the best library in terms of performance for each device. So in the case of the CPU, we are using Intel MKL, and in the case of the GPU, we're using Q+. So when HPHL has replaced all the intrinsics by native calls, HPHL is going to generate the binary executable, and it always uses the CPU LLVM backend, even when the GPU is selected. So in this table, we can see some examples of HPHL functions. We have malloc, memcpi, and general matrix multiplication. And in this table, we also can see the HPHL intrinsics that gets generated in the intermediate representation. So all of those functions always need an argument that is the device in which the function has to be executed. And the device can be selected using one of the defines that you can see below. For example, HPHL device CPU for the CPU, or HPHL device GPU for the GPU. So here we can see a real example of an HPHL program. The first thing to do is to include the header. The second one, we define the device that we're going to use, that in this case is the CPU. Then in the code, we have the initialization. We have the allocation of the memory of the matrices using HPHL malloc device. Then we must copy the memory from host to device using HPHL memory device. We do the general matrix multiplication, and we copy back the results from the matrix. So in the case that this code is going to be run on the CPU, like is this example, then the HPHL memcpi device are going to be translated by the HPHL into a non-operation, because it doesn't make any sense to copy the data from the CPU to the CPU. But in the case that the device selected is the GPU, then those calls are going to be replaced by library calls of CUDA, which essentially is going to be CUDA memcpi and CUDA malloc. So now we're going to evaluate our approach. For the CPU, we have used two Intel Xeon Gold, and for the GPU, we have used an NVIDIA 280 Ti. We have compared HPHL against WinAPI and FAST. So the thing is, HPHL, as I mentioned before, uses MKL for the CPU and QBLAST for the GPU. And the same happens with WinAPI, because WinAPI uses one MKL for CPU and GPU, but under the hood, one MKL is using Intel MKL and QBLAST for the GPU. And the FAST library uses handcrafted code as the CPU backend, and as the GPU backend uses QBLAST. So in the CPU measurement, we can see that the native implementation of the general matrix multiplication using MKL is a bit faster than our HPHL approach, but it is very close. And then we have WinAPI, which is a bit far from HPHL. And then we have FAST, which is much slower. And in the GPU, we can see much or less the same, but on the GPU, we were not able to measure the time from FAST due to a problem in the time measurement itself. So as we can see, there is an interesting issue, because in the GPU, we achieve the same performance as the native implementation, but on the GPU we can observe a little variation from the times, and this is because we have compiled the native application using GCC, and we have compiled the HPHL program using Clang. And this is essentially the big difference between the performance that we obtain in the first case and in the second case. And we have observed that because we also tried compiling the native program with Clang, and we obtained the same results as HPHL. So as our final conclusions and future work, we have seen that HPHL outperforms the rest of the presented alternatives for general matrix multiplication. And we believe that optimal performance is possible when targeting multiple devices with a single source code, with a single source multiple devices languages. But the key here is to use optimized libraries for each architecture if we want to exploit all the performance of the device. And we believe that this language, the HPHL language, is a promising approach to achieve great performance while providing an easy programming interface for heterogeneous computing. So for future work, we are planning to add support for AMD GPUs and also Google TPUs. And also we would like to implement a new function and functionality to be able to run the parboil benchmark. So we are capable of comparing HPHL against HPVM in the future. So thank you very much for your attention. I hope you found these ideas as interesting as I do. And I'm ready to hear your questions.